Okay, before we're going to apply Snell's law of reflection and refraction to solve geometrical optics problems, let us take an alternative look at how one might derive the Snell's laws for both reflection and refraction. And this is first proposed by the French mathematician by the name of Fermat. You probably have heard the famous Fermat's last theorem. It's the same Fermat. He gave us a highly elegant way of looking at the laws of reflection and refraction. Both the laws of reflection and refraction actually follow the same simple guideline, the so-called Fermat's principle. And that principle is very simple. Suppose you have a starting point and you have a finish point, and somehow light has to travel from here to there. Okay? Light has infinite number of ways to choose, infinite number of possible paths to choose to go from here to there. What is the actual path chosen by light? According to Fermat's principle, the idea is very simple. Light always picks up a path, an optimum path, which will allow it to travel from the starting point to finish point in the shortest possible time. Okay, that is the famous Fermat's principle. It's very elegant. It doesn't matter whether it's reflection or refraction or anything. Suppose I have a uniform medium, right? A uniform medium. The speed is the same throughout. Now you shoot a beam from this point and aim at that point. You know light is going to travel in a straight line. You're not going to see light bending around like this. Why? Because that's Fermat's principle. Light tries to get from here to there in the shortest possible time, and since the speed is not an issue, the speed is the same everywhere. Shouldn't you then pick up the shortest distance to achieve the shortest time? So therefore, light will automatically travel in a straight line. Okay, so light always travels in straight lines within the same uniform medium in which the speed of light is the same. If you see a light being bendy, what does that tell you? It must be traveling through a non-uniform medium in which the speed of light varies from point to point. Okay, so that's Fermat's principle. And let's see how the Fermat's principle would help us understand or derive the laws of reflection and refraction. Let's see here. In the case of reflection, okay, light cannot travel directly from here to there. Rather, it has to somehow reflect first, pick up a landing point, reflect first, and then go to the finish line. Okay, so it's got two lengths, 1 and 2. The question is, which point will the light pick up as a landing point so that it will go from here to there? We know the correct way is the way that satisfies Snell's law, right? Snell's law, which says that the two angles, the angle of incidence and the angle of reflection, would be the same. Okay, and let's find these two paths. Let's say we have this line here, and then we have this line. Okay, so light comes in and reflects out. Now the way I draw it, obviously the Snell's law is not quite satisfied because this angle and that angle are obviously not the same. I want to show you that this is not the choice in accordance with Fermat's principle. If you want to follow Fermat's principle, okay, then since everything happens in the same medium where the speed of light is the same, to get from here to there through reflection in the fastest possible time, which is what Fermat's principle says, the length, this red length plus this yellow length must be what? Must be the shortest possible, right? Must be the shortest possible. And is this really the shortest possible? Well, let's see. There's a common trick that we use when it comes to when there's a mirror like this. The common trick is you want to find the mirror image point. Okay, so I'm going to find the mirror image point right here. Okay, of this guy. Okay, so this is the mirror image of that point. Right? So that means these two distances are the same. Okay. Now what I'm going to do is I'm going to connect this mirror image to the finish line. I'm going to connect this, and I'm also going to connect that. Okay. Suppose that is the actual landing spot. Okay. What I want to show you is that this is not the right landing spot. The right landing spot should be here. How do I show that? Because, look, Fermat's principle tells us that the red path plus the yellow path has to be the shortest possible, right? On the other hand, this red path has the same exact length as that green path, right? Because look, this is the mirror image of that starting point. So these two right angle triangles are congruent triangles. Okay, so that means this red line and this green line are equal. So that means the total path length, if you try to land at that spot, would be this one plus that one, right? Remember that. It's this one plus that one, which is of course longer than that straight line, right? It's longer than that straight line because it's a triangle, you know, that's the third side. On the other hand, if you try to land at that spot, okay, so now the red line is going to go here. And the yellow line is going to go there. It's going to go there. I say this is a better choice. Why? Because this red line is the same length as that green line, right? From here to there. And this yellow line is another part of the path. So if you land here, then the total distance traveled would be this plus that, which is the same as this plus that. It is just this whole segment of length, which is shorter than this plus that, which is the same as this plus that. Okay, so what does that tell you? It tells you the optimum landing spot is right here. It's right here. This is going to be the shortest traveling distance of this path plus that path. And what's so special about that path, about that point? That point, look at that point. Okay, first of all, these two angles are the same because these two triangles are congruent triangles. And secondly, you have a straight line here and a straight line there. That tells you these two angles are also equal to each other, right? So that tells you that this angle equals that angle. And that, guess what? That is the law of reflection, isn't it? That's the law of reflection right here. Okay, so we have come to an understanding of the law of reflection using the Fermat's principle. Now, what about the Fermat's principle for refraction? Okay, for refraction, I'm going to leave this as an exercise for you. I'm not going to solve the entire problem, but I can set the problem up for you and you can see it for yourself. Okay, first of all, in qualitatively speaking, suppose V1 is greater than V2. So this is say air and this is water. Okay, so light travels faster in water than in air. Okay, what happens? Okay, now, and suppose you have a certain starting point. You have a certain starting point, and you also have a certain end point. You can choose any. You can choose any point to start, any point to end. You can pick up a certain coordinate here, a certain coordinate here. It doesn't matter. Light somehow has to make its path from here to there. Okay. Now, let's say we choose these 2 points such that if you draw them, a line connecting them, you're going to get it will pass through a certain normal line. It's just for simplicity, for convenience. We're going to draw something like that. Okay. Now, imagine if air and water, if these two media have the same speed of light, of course, which they don't, right? If they did have the same speed of light, then the simplest way for light to travel from here to there would be simply follow that straight line because the shortest distance between the 2 points, which also translate to the shortest possible time because the speed is the same. On the other hand, we know light travels faster in air, slower in water. Okay. When you consider that, when you consider difference in speeds, how would you adjust the path of light so that it goes from here to there in the shortest possible time? Well, you can try to go this way. And my question is that a good idea? Well, obviously you're going to travel longer overall distance, right? Longer overall distance. And you see, you travel shorter distance within the first medium and longer distance within the second medium. That is not a good idea, folks, because light travels slower in water to begin with, and you want to let it travel further distance with a slower speed. That is only going to increase the total time, isn't it? So this path is not even as good as the straight line. Is there a better alternative? Yes, there is. What you can do is you can first travel to some point here, and then you travel through there. You see, price you pay is that the total path length of this green path is longer than the straight line. But we don't care about the path length per se. We care about the total time, right? Okay, the advantage is that, you see, light will travel a longer distance in air, but a shorter distance in water compared with a straight line path, right? And overall, that is advantageous because light travels slower in water than in air. So you give it less distance to travel, so it doesn't really cost you that much time, even though you have a slower speed. Okay, you give it longer distance to travel in air, but light travels much faster in the air than in water, so it doesn't cost you that much extra time. The overall time is still shorter. So you will end up with a path like that. And clearly, this angle is greater than that angle. So it agrees qualitatively, okay, with the analysis of Snell's law, which says theta 1 has to be greater than theta 2 when you have when light travels from air to water. Now, how do you get the actual expression sine theta 1 over sine theta 2 equals to v1 over v2 or n2 over n1? How do you get that? Well, to get that, what you have to do is you have to, just like we did here, we have to pick up an optimum landing spot. Okay, so light first travels to that landing spot and then it goes on to the next segment. You want to pick up this optimum landing spot so that the total time it takes t1 plus t2 will be the shortest. Okay, so what you need to do then is imagine you have this coordinate, that coordinate, they're all fixed, they're all given. Okay, I want you to then find a certain distance we call x. Given x, you will know that distance, right? That's given. Okay, you choose a certain distance x. Given that x, you can find this t and you can find that t, right? And you can add them together, t1 plus t2. They will be a function of x, which is from here to there. And then what I want you to do is I want you to optimize t1 plus t2 as a function of x so that t1 plus t2 is a minimum. You can achieve that by taking derivatives, of course. Okay, the total time, big T, which is t1 plus t2. You take the derivative of big T with respect to this x from here to there. That, and set that derivative to equal to what? To 0, of course. Okay, and then the outcome of setting this derivative to 0, which is the minimization of total time, turns out is just sine theta 1 over sine theta 2 equals v1 over v2. It is the same as the Snell's law for refraction. So the Fermat's principle really teaches us how light picks up a path under any circumstance. Okay, there is only one guiding principle, that is, light always tries to get from here to there in the shortest possible time. I wish people are that smart all the time. Okay, now let's discuss an interesting phenomenon associated with the Snell's law. It's called dispersion. You noticed I use different colors to spell out that word dispersion. What is dispersion? Well, you know, the light from the sun is white. That means it actually consists of many colors. It in fact encompasses all the colors in the visible light spectrum. Different colors corresponds to different frequency or different wavelengths. Okay, and the thing about different wavelengths or different frequencies is that as waves of different frequency travel through vacuum, electromagnetic waves, they all have the same speed, the speed of light. It has nothing to do with the wavelengths. On the other hand, when these different waves with different wavelengths, they travel through a medium such as air, such as water, such as glass, they will break up into different speeds. Okay, the wavelengths will be a factor in determining the speeds. In general, it's because of the interaction between the molecules in the medium and the wavelengths, and the wave. Okay, and when the wavelength is shorter, such as violet light has a shorter wavelength than red light, of course. When the wavelength is shorter, it will spend a greater number of wavelengths traveling through the same thickness of a medium. Make sense? Okay? And with each wavelength, it will interact with the molecules to a certain extent. So generally speaking, a wave with shorter wavelengths, such as violet light versus red light, will have greater amount of interaction, activity with the medium, such as glass. And if the glass tends to bend the wavelight, okay, it tends to bend the light towards the norm. It's going to do so a little bit more for purple or violet light than it would do for red light, because it interacts more strongly with purple light or violet light simply because it's got a shorter wavelength, so it spends more number of wavelengths traveling through glass. Okay, so you can imagine something like this. You can imagine you have a beam of light, okay, a beam of white light coming in. Here is glass, and here's air. You got a beam of white light coming in, which has all kinds of colors, okay, all kinds of colors. Because of the refraction, it's going to bend towards the norm. But which light is bent more than other colors in visible light? Well, it's got to be purple, okay, because purple has the shortest wavelengths. So purple is going to be bent a little bit more. And the next one will be blue. I don't have all the colors, but if I did, I can draw somewhat better. Okay, and then you have green. Okay, you have green. Of course, I exaggerated. It's not that bad. Okay, and then you have yellow, and you have orange, and finally you have red. Red has the longest wavelength, so it spends the least amount of wavelengths inside glass, and therefore the bending is the least significant for red. So you see, the same beam, which consists of all kinds of colors mixed in, which appears white, is now going to be separated into different colors. Okay? A device that does so, that separates colors from sunlight, is called a prism. In fact, Newton, Sir Isaac Newton, the same Newton, was the first person, documented person, who used a prism to separate colors from the sunlight. Okay? And when you see reflections or refraction from crystals, you see multiple colors. This is not because the crystal itself has multiple colors. It's because the crystal can cause dispersion of white light. Okay, it takes beam of white light and separates white light into different directions because it has different indices of refraction for different colors. Okay, so light will travel in different directions, or they have different speeds according to their frequency. This phenomenon is called dispersion. It's called dispersion. Dispersion is responsible for for a wide variety of natural phenomena, including, for example, a rainbow. Okay, so in the case of a rainbow, you get white light coming in from the sun, right? How do you get a rainbow? You need two things. First of all, you need a light source, which is sunlight, and secondly, you need moisture, right? It happens, say, after a rain. Okay, after rain, the sky is still saturated with moisture, which means tiny droplets of water. Tiny droplets of water. So imagine you got a beam of white light coming in, okay, and after getting refracted by the drop of water, different colors are going to separate into different directions. Here is you have red light here going this way, and then you have purple light and the green light